Hello there. Welcome to part 2 of logistic regression stuff. Yeah. So, part 2. So in the last video we talked about how we evaluate models 3 ways. With visuals, with estimates, and with model comparisons. And oftentimes we don't have a way to compute estimates or model comparisons-ish, or to visualize the models. And I started talking about logistic regression, because logistic regression is like difficult in some ways. Particularly with the estimates, because we have to start interpreting odds ratios. So yeah, we're going to be talking more about logistic regression. So as you may remember, logistic regression is used to model binary outcomes. Like the probability that you will exit my video within the first 30 seconds. Yeah, we got estimates. And when we are talking about estimates in logistic regression, they kind of don't make sense, because then we're talking about the log of the odds or the odds ratio. Here's the thing. Odds are odd. And odds ratios are odder. It's really hard to understand what's going on with odds. So I know we talked about some of this last week, but I'm going to go into a little bit more detail just because I feel like it. Why not? And they're not the same as probabilities, and it's easy to get them confused. So let me just give you an example. Why not? Let's say the probability of an event happening is 10% or 0.1. The odds is going to be p divided by 1 minus p, or in this case, 0.1 divided by 1 minus 0.1, which is equal to 0.111. So if p is equal to 1, the odds are 0.111. Now, when we are doing logistic regression, we are not modeling probabilities. We are not modeling odds. We are modeling the log of the odds. And so when we take the log of the odds, in the previous example, when it was 0.111, if we take the log of that, it gives us approximately negative 2.20. And the problem is that log odds may be linear, but the probabilities are not. What do I mean by that? Let's just say that we add 1 to the log odds. So if we take that previous value, negative 2.21, and add 1 to it, then we're going to get negative 1.20. Now, what does that translate to in terms of odds? Well, if we go e to the negative 1.2, that'll give us the odds, which is approximately 0.3. And we can then convert that to a probability, 0.23. So what we are seeing here is a 1 point change in the log odds from negative 2.20 to negative 1.20 is a 1 point change in the log odds, but the odds change from 0.111 to 0.3, or almost a 0.2 increase. Probability, on the other hand, goes from 0.1 to 0.23, or a more than 0.2 increase. Now let's go ahead and start at a different value. Let's say that instead of starting at p is equal to 0.1, we're going to start at p is equal to 0.5. And so the odds end up becoming 1, and the log of the odds equals 0. Now if we add 1 to the log of the odds, as we did before, so going from 0 to 1, we get an odds value of 2.72. So our odds went from 1 to 2.72, so they more than doubled. And then the new probability, what used to be 0.5 is now 0.73. So what we are finding is that a 1 point change on this specific area of the log odds scale results in dramatically different changes in probability and changes of odds. And we would expect that. So they are not really proportional to each other. And just to give you an idea of what happens with logs versus odds versus probabilities, take a look at this table, which is going to show you different probability values and their corresponding odds and their corresponding log of the odds. So why am I going through all this? Just to tell you that, just to confuse you, I'm really trying to show you that odds ratios do not directly translate to fixed changes in probabilities. So when we exponentiate the coefficients, which are on the log odds scale, we convert them into odds, and we could talk about percent changes in odds, but that says nothing about probabilities, because a percent change in the odds isn't the same as a percent change in probabilities. Basically, I'm trying to illustrate that it's really hard to interpret logistic regression models. And another problem with logistic regression is that the intercept is like meaningless. Like the interpretation of the intercept is it is the expected value of the log odds of y when x is equal to 0. Like, I don't have an intuition for that. So there's nothing intuitive about it. And with some effort, you can interpret the odds ratios, but you have to do a lot of mental gymnastics. So I'm going to introduce something new. What I think is a more intuitive way to interpret regression coefficients. But first, a word from our sponsor. Me. Hey, you should totally take a simplistics class. Did you know that in the month of May, every Monday in May, the first 4 weeks of May at least, we have a new class about data visualization and machine learning, data mining, random forests sort of thing. It's going to be amazing. It'll be the first live class I've ever taught of it, and you're not going to want to miss this. In fact, if you do, you might die. Of course, you might die if you do take the class. Well, you're going to die anyway. I'm not going to say that it will prevent death to take my class, but I'm also not going to not say it. Just something to think about. So yeah, if you're interested in taking a live class with me or even a self-guided class, I'll leave links in the description below. And oh, by the way, did you know that I do consulting now? Yeah. You want to be consulted? You want to consult. You want to be the recipient of consultation services. I'm sure there's a way more elegant way to say that. If you want to be, if you want help from me, that's an easier way to say it, then visit the link in the description. All right. Are we done with our commercial break? I don't know who I'm talking here. I'm definitely home alone right now. All right. Yeah, we're done with our commercial break. Now, let's talk about new coefficients. So yeah, new coefficients that I'm going to interpret, or new estimates, or new mathematical concepts that are fun and interesting. So I cannot say that I invented them, but I can almost say that. There's something in item response theory. For those of you who don't know about it, I'll leave a link in the description about item response theory. And basically, they have like a regression or a logistic regression like curve, and they offer like intuitive interpretations of what a slope and an intercept are. And so I started thinking, man, why don't we have that for logistic regression? And then after doing some math, and I'm going to leave that on the screen, and I'm not going to explain it because like 3 of you will care. So now we have for logistic regression similar interpretations. So I'm going to introduce 2 things. One is what I call the instantaneous slope, and the other is what is called the threshold. And these 2 values provide much more intuitive, what I think, interpretations of a logistic slope and a logistic intercept. Now, if you look at a logistic curve, the slope changes depending where you are in the function. So it doesn't make sense to talk about a single slope. Instead, we're going to pick a point on this line and talk about what's called the instantaneous slope. If you're familiar with calculus, you'll get this idea pretty easily. If not, then stay with me. Basically, the slopiness of the line is changing. So at this particular point, the instantaneous slope, or the tangent slope, is this. And at this point, it is this. And so what we're going to do is we're going to create a new estimate that tells us what the instantaneous slope is at p is equal to 0.5, or at the 50% threshold. Why that threshold? Well, there's 2 reasons, or there's 1 reason. I think it's just 1. Because that is the point of maximum steepness on that curve. Or in other words, I'm going to tell you the slope at the steepest point of the logistic curve. That's way more easy than interpreting things in terms of log of the odds. So in this example, if we follow the line at p is equal to 0.5, again, that is the maximum slope of that line. And it just so happens that the slope is at 0.12. Or in other words, a 1 point change from x equal to 0 to x equals 1, we would expect a corresponding change in probability of 0.12. Or in other words, at around an x value of 0, we expect people to change at a rate of 12% probability increase for every point they change on x at that specific point. So that is a IRT, item response theory, like interpretation of a slope, or an instantaneous slope, or a tangent slope. What about an intercept? Well, we can convert the intercept because in logistic regression, intercept doesn't mean anything intuitive. But instead, we're going to make it mean something intuitive. And so what it means for our purposes in this video is if we do a little math, again, here's the screen. Ah, scary! We can use that mathematical information to come up with a way more intuitive interpretation of the intercept. And so what the intercept here is, it's called threshold in item response theory, and we're going to use the same terminology here. The threshold is the point at which the predicted x value is 50%. So in this graphic, which we saw earlier, the threshold is at 0. So that tells you that when x is equal to 0, your probability is at 50%. Or another way to think about it, it is the value of x where 50% of the people will have a 1 and 50% of the people will have a 0. And that's kind of informative and kind of cool. Let's look at some other examples. So here we have a steeper slope. We have a 0.25 slope. Or in other words, a 1 unit change indicates a 25% increase in the probability of getting a 1. And the threshold is still 0. And here's one where the slope is 0.5 and the threshold is still 0. Oh, but snap, we done changed the threshold. So now we see a logistic curve, which looked like what we had before with a 0.25 slope, but now the threshold is at -2. Or in other words, 50% of people who score a -2 on x are 1s and 50% are 0. And then here's an example where the threshold is equal to 2. So you get that? Pretty cool, huh? So yeah, I think that's way easier to interpret than what we had before. Yay! So that's the basic idea. We're going to take the existing logistic regression parameters and make them much more intuitive and easier to interpret. So let's go ahead and step into R and see how this applies. Shall we? Let's look at the new estimate, shall we? Oh, let me make the screen a bit bigger for you. There we go. All right, so the question that we want to ask, this is the table saw injury dataset. And why do I have a table saw injury dataset? I made it up. Why would I make up a table saw injury dataset? Because back in 2016, I cut off the tip of my thumb. You want to see? It's not like bloody right now, obviously. See if the camera's going to focus on that. Oh. So my left thumb is a 1/4 inch shorter and like 68.4% uglier than my right thumb. And so what do you do when you're a statistician trying to think of fun data sets? You think of Morbic table saw injuries. So what we want to look at is we got this data set called table saw injury, which is part of the FlexPlot package. And if you want to look at that, you can go ahead, tablesaw.injury. And we've got safety scores, attention scores, gender, and whether they have been injured. And for the purposes of this data set, an injury means any sort of accident that requires a hospitalization of some sort. Obviously, I've had one. But let's see what happens to other people. So what we want to know is what is the effect of safety on injury once we control for attention. So let's say we're evaluating their safety score, which maybe theoretically, like, their attention can't be controlled. People have like natural attentiveness, and you can't affect that, but what you can affect is their safety rating. We are evaluating people on their safety scores, and we want to see if you control for the thing that we can't control for, which sounds kind of funny, can you actually affect people's probability of getting injury by making them more safe? So let's go ahead and look at the univariate distributions, just because that's what we like to do. So safety scores, centered on 10, range from about 0 to 20-ish. And then attention scores, we've got ranges from approximately 0 to 75, but we got somebody with a -25 or more, like negative 30-ish, something like that. Not sure what that's about. If this weren't a simulated data set, I would investigate that, but it's a simulated data set, so I'm not going to investigate that. Now I'm going to look at injury, and it seems that, by the way, I imagine this is like a bunch of woodworkers, and half of them have had a table saw injury in their life. I don't know if that's realistic, but it actually wouldn't surprise me. Like, woodworking is a dangerous hobby. Ask me how I know. Oh, you already know how I know. So we're going to go ahead and fit the model, predicting injury from attention and safety, and then we're going to visualize the variable of interest, and we see something that looks like that, and that's kind of interesting. Cool. So yeah, there's a very strong relationship between safety and injury, such that the higher your safety, the lower your probability of injury. Shocking. Now let's look at those new coefficients, well as the old ones. So for some of these, I'm going to ignore the raw estimates, the unstandardized estimates, because safety is an arbitrary scale. But instead, we're going to look at, we'll start here. So standardized estimates, we've got an odds ratio of 0.509. What is that telling us? That is telling us that a 1 standard deviation increase in your safety score corresponds to a 49% drop, which is 1 minus 0.509 in the odds of getting injured. So that's significant. And I don't mean that like statistically significant. That's just a big change. So your odds cut in half when you increase by a full standard deviation. That's pretty cool. And prediction difference. We're going to look at that other metric. So that 0.33, let me make that a little bit bigger and run that again so it shows up all the way. So prediction difference, it gives you a little bit of a hint. Oh, and by the way, this is new. Like this, all this stuff is pretty new in FlexBot because I just created this and it's pretty cool. So if you want to see an explanation of what all these numbers mean, you can go type estimates.glm, like it says in the documentation there. Oops, if I could spell estimates right. And right down here, it shows you what all these values are and how to interpret them. But we are going to go with prediction difference. So basically what that's doing is it is predicting the probability of getting injured for somebody who is 1 standard deviation below safety versus 1 standard deviation above safety. So they're basically 2 standard deviations apart. And we want to see how much their probabilities change. So it's a 33% decrease from negative 1 standard deviation to positive 1 standard deviation. That's pretty big. So if you can increase your safety score by 2 full standard deviations, you're going to reduce your chances of getting injured by 33%. That's pretty cool. Holding attention constant, by the way. Now let's go ahead and look at the IRT-like estimates. So we've got a threshold value of 10. What does that mean? Remember, again, what the threshold tells you is it tells you the point on X where 50% of the people get injured, in this case. And we can see that if we overlay a plot. And basically what I'm doing is I'm saying visualize the model, and I'm visualizing safety on the x-axis, injury on the y-axis, and I'm adding an x-intercept, so I'm adding a vertical line at x equals 10. Just, where did I get that 10 from? I just got it from the threshold. I just want to show you that this is going to intersect with the 50% threshold. And boom, there it is. So we see that, again, that's exactly what that value means. That new intercept tells you the point on X, or in this case safety, where 50% of people get injured. And it happens to be for a safety score of 10, which looks like it's about the mean, which is kind of interesting. So those of average safety, half of them, we predict on average will get injured and half of them will not. Now let's go ahead and look at the next value, which is the instantaneous slope. Let me make that big again. And so we got instantaneous slope, negative 0.084. And again, these are probabilities. So what is that telling us? That is telling us that around that 50% threshold, or the maximal point of steepness or discrimination or differentiation, is 8 percentage points per 1 point increase in safety. So basically, and since this happens to be around 10, around the range of 10, a 1 unit increase in safety means that you are dropping your probability of getting injured by 8.4%. That's kind of cool. And to see that illustrated, I'm going to plot the same thing I did before with the intercept, but now I'm going to overlay a slope of negative 0.084 because that's what we computed from here. And this intercept is totally arbitrary. I was just trying to find a point at which it would kind of snuggle up next to that logistic curve. And so we can verify. So that gray line is the line that I added. And not surprisingly, around that 50% threshold, those two lines are parallel. Which again, that's what we would expect. Which is exactly what should happen. Because that's what the estimate is telling us. It is telling us that around the center, that a 1 point increase in safety means an 8.4% decrease in injury. So these are really cool estimates. Really cool estimates. Let me give some caveats though. One is that if you have a categorical variable, things might not match up. Let me show you what I mean. So I'm going to add gender as a predictor and then look at the estimates and then do basically what I did before. So I'm going to look at the estimates and then I'm going to find 8.91 for the threshold. And so if I were to plot that and put an x-intercept at 8.91, they wouldn't line up. And by the way, I got tricked. I was like preparing this for this video. I'm like, why isn't it lining up? I couldn't figure it out. And then I realized, oh, we have multiple genders in here. Because what it's doing in the background is anytime you're estimating the slope, it has to do something with the other variables. So you remember how I said holding things constant? Another way to think about it is assuming somebody is at the mean, what is their predicted value? Unfortunately, when you have categorical variables, there is no mean that you can compute. Instead, you have to arbitrarily pick a category, which is what this is doing here. And apparently it's not picking the category that corresponds to that line. So instead, if I use this R code and show gender and then do that, lo and behold, that does intersect at the 50% mark. But for the females. So that tells you that that threshold corresponds to the threshold for the females. And I guess the males would be different. It might be, looks like 10.5 or something like that. So that's one caveat to be aware of. Another one is that sometimes the IRT estimates will give you predicted X values that are beyond the range of X. So maybe your X variable ranges from 1 to 100, and it might give you a threshold that's like 500. Okay, that can happen. What would that mean? Well, let's look at an example. So if I do back to the Avengers data set, and if I look at the estimates for willpower, then I get 312. Now if I actually visualize the model, willpower only goes from 0 to 120. So it doesn't reach the threshold until you get to 312, which is like more than double what the range of willpower actually is. Basically what that tells you is this isn't a good predictor because it never reaches a point where it has maximal discrimination. Although there may be exceptions to that. I guess if you have a situation where it's very rare for something to happen, which is what we have in this case. Oh, that's interesting. They got died at the bottom and no at the top. Normally it's the other way around. But anyway, whatever. So yeah, if you have a rare event like you do in this one where the number died is far fewer than the number who didn't die, then you can have that happen. So that's something new that I added to the FlexPlot package, which I think is really cool and intuitive to use. So let me give you some pros and cons of these new IRT-like estimates. Pros, they give an intuitive interpretation that are in terms of probabilities, which is nice. They're much easier to explain than odds or odds ratios or log of odds to a non-technical audience. And also, they're already used in item response theory, and they seem to be beneficial there, so why not here? Part of the problem with these is that you have to have some understanding of like tangents, or you don't even have to know the term tangents, but instantaneous slopes and the idea that slopes are changing and then it's a conditional slope. It's only at the 50% mark. So that is a little hard to wrap your mind around. But you know what? Might as well have them because they're kind of useful. And also it has some issues with the categorical variables because then it has to randomly pick a group. And it also might give you estimates that are beyond the range of X. So yeah, those are some problems. But hey, it's not like it costs you anything to compute it. Well, I guess fractions of a cent in electricity, because adding those to the FlexPlot package increases the computational intensity of the estimate marginally. But hey, they're there. If you want to use them, use them. If you don't want to use them, I don't care. Anyway, hopefully this has been helpful. Hope to see you in a class. Hopefully May. If not, hopefully some other time in the future. Hey, great hanging out with you. Hope you had fun. I had fun. Good. All right. Peace out.